So the third talk for today is private collection matching protocols, and the presenter is Kasra EdalatNejad from EPFL. Take it away, Kasra. Sorry to interrupt. I think your microphone is not working.
Thanks. So when we're working on different problem, we noticed the same pattern repeating over and over, where we had a client with a single set who wanted to determine the utility of a collection of many sets held by a server. For example, when we were working for document search for investigative journalists, we had a network of hundreds of journalists who had thousands of documents on their computer. Now, one of these journalists wanted to come and ask a query about an interesting topic of investigation, and the system needed to find another journalist who have documents relevant to this investigation. Then we could put them in contact, and they could decide whether they wanted to do a collaboration. An easy way to see how to perform this search is using private set intersection cardinality, where you have a query, you represent it as a set of keywords. And you can do the same transformation on documents that you have, and in the end, you just see how much they have in common and decide whether this document is relevant or not. But as you can see here, we are revealing a lot of information about every document that this journalist has. And ideally, we would want to have a more private search where it just gives us a binary answer. Should I contact this other journalist? Which can come from a question like, does he have at least one relevant document for me? Or a more stricter, I want to collaborate with someone who has at least T documents that I'm interested in. Another problem that we saw in here was like chemical compound search, where chemists can accelerate the research by having properties of compounds similar to their research target, and they are willing to pay a lot of money to buy chemical compound data sets as long as they have similar compounds in them. And based on other problems like this, we introduced a new class of problem, which we call private collection matching, or PCM, where clients want to compare a single set to all n sets held by a server, and clients are interested in the collection-wide utility and do not need to have an answer per every server set. And finally, both the client and the server want to have privacy. However, this problem differs in the ways that when a server set is of interest to the client, or how to combine these sets together. Now, let's elaborate the requirement a bit more. First, PCM protocols must be able to compute flexible matching criteria without revealing intermediate values such as intersection to the parties. For example, a document is relevant to the investigation if it includes all queried keyword or a threshold of them. Next requirement is that PCM protocol must be able to aggregate many server set responses without leaking information about individual sets, such as just give a binary answer, is at least one relevant document in this data collection, or how many relevant documents this journalist has. And finally, we have the problem of extreme imbalance, where our clients have limited computation and communication power. And the server's input size can be 1 million times larger than the client's. For example, just searching a data set of 1 million compound give you this large difference. As I mentioned, PSI cardinality before, these problems are really close to set intersection, and we try to see, can we use existing work to solve this? First, we tried approaches based on like comparisons such as oblivious transfer, OPRF, or polynomial evaluation, but they could not satisfy our privacy requirements because they are always revealing the intersection or its cardinality. And it's not possible to aggregate their response in an encrypted domain. Fortunately, we have approaches that can do this, like Circuit PSI or generic SMC, where you can compute arbitrary functions on top of intersection. However, these approaches had an inherent problem of client computation and communication costs dependent on both the client and server input sizes. So unfortunately, they could not solve our problem. Now let me give you a bit more of a formal view of what's happening in here. In PCM problems, we have a server with n sets that is good for representing our documents. And we have a client with a single set that can represent our query. Then we want to perform an arbitrary matching that in here, let's say, we want to see are all queried keyword inside the document and get a binary answer out of this. Is ith document relevant or not? And finally, aggregate all these n binary values to give a collection-wide response, should I contact this journalist? And for the properties that we want, it's correctness, client privacy, and server privacy. And we go with the typical MPC definition of privacy, as our protocol should not reveal any information beyond the intended output of the protocol. And to solve this, we design a modular framework for PCM problems, where in the first layer we have set intersection and cardinality, and we optimize it for two scenarios. In the first one, the size of the client set is very small. For example, in document search, normally queries have less than 10 keywords. And in the second scenario, we assume the domains of set inputs for both the client and server are small, since that's how we can represent chemical compounds. In the next layer, we have matching that we decide when a server set is of interest to the client. And the two interesting approach in here is like the full matching that we say all queried keywords are in a document. And then we have a threshold variant that says that, oh, we have at least t common elements. And finally, in the last layer, we aggregate these responses with different policies. For example, in existential aggregation, we check, does at least one relevant document exist? Or we can do cardinality and count the number of relevant documents. And in this talk, due to lack of time, I'm only going to explain the variants that are useful for our document search. And we built our protocol on top of somewhat homomorphic encryption, which have the generic key generation, encryption, and decryption functionality. And I use a double bracket notation for showing encrypted value. And the only important part is that we can perform addition and multiplication modules a prime number in the cipher domain. So let's start building our protocol. We have a client with a set of m input keyword, and they first encrypt them and send them over the server. Then in the server, we base our intersection on oblivious polynomial evaluation, where we represent the server sets as roots of a polynomial and evaluate the client point on this polynomial. And if one of these terms is, if the client input is inside the set, one of these terms going to be 0, and we are going to have a 0 p of I. And otherwise, due to this randomizer R, we are going to have something completely random. And we can repeat the same process for all client elements and get a set of PI values. And for full matching in here, we just perform a summation over them. The case that we are interested in is that all input elements are inside the server set, so all of them needs to be 0. So the summation will be 0. But if any one of them is not inside, we are going to get something random. There is a bit of problem in here that if we have more than 2 elements outside, we may have false positive that we will discuss in the paper. And we can perform the same operation over all sets that we have that leaves us with n interest values, lambda i's. And as you remember, if a document is interesting, it's going to be 0. And to check if at least one of these documents are interesting or have a 0 value, we just compute the product. It's only going to be 0 if one of the documents is relevant. Okay. And in the final phase, the server just sends back this encrypted answer to the client, which can decrypt and use. In the paper, we discussed the security and privacy of our scheme. We show that in the semi-honest setting, we provide correctness, client privacy, and server privacy. And in the malicious setting, we provide client privacy and some limited form of protection against specific behaviors in the malicious setting for server privacy. We have implemented our scheme using BFE somewhat homomorphic encryption using the EdalatNejad library, and we heavily rely on SIMD batching and replicating the client query. Our code is available online, and you can access through this QR that I'm going to show again in the conclusion. To evaluate our system, we compare against two document search alternatives that are based on the generic solution that can achieve the same privacy as our solution. One of them is based on generic SMC, and we use a Garble circuit to build it. And the second one is based on the state-of-art circuit PSI paper that was presented here last year in PETS. And in here, I'm showing you the latency, client computation, and the transfer cost of searching end documents with our system noted in green, and related work shown in blue and red. And as you can see, we are always outperforming them, but when we look at a specific case of 1,000 documents, we are drastically improving client computation, latency, and transfer costs. To wrap this up, in our paper, we studied the requirements of 3 practical problems and introduced a new class of problems called private collection matching. We designed and implemented a modular framework that drastically improved latency, client computation, and communication. However, we need to acknowledge that while our protocol works very well in theory, there are some practical limitations that not all combination of our framework is practical due to reliance on an expensive zero detection functionality, and we had to optimize our solution to bypass the need of this function in our practical systems. Thanks for listening to my talk, and I'm open to questions.
Thank you very much, Kasra, for the talk. Excellent talk. Let's get the other speakers set up while we ask Kasra some questions. So another question from Dimitris Mouris here on the Zulip. Do you consider a malicious server? I think you may have covered that at least partially in your presentation. What if the server sets A to be just one file instead of the aggregation of multiple files?
So let's start with the first one. So for the server, it goes for our client privacy, and yes. But in here, the reduction is very simple because server only receives a encrypted value, and he never sees any decryption or any other interaction. So it was straightforward. And can you repeat the second question?
What if the server sets A to be just one file instead of the aggregation of multiple files?
So one of the limitations in here is that the server can not follow the computation or even directly put the answer that he wants in the encrypted output, and our protocol does not prevent this. So if the server is malicious, we do not provide correctness, but to some degree this was not fully unintentional, because when the server can choose his input, he has a lot of control over the output of the computation, even when he's performing them honestly.
One very quick question from me, actually, just very quickly. Have you had any success in reaching out to like journalistic institutions, real-world use cases? Can you maybe like summarize that in 30 seconds?
Yes. So actually, the use case for journalists was from a previous paper that we did together with International Consortium of Investigative Journalists, where we deployed a document search for them. They have interest in achieving these level of privacy, but due to the scalability and deployment costs, we at the end decided to go with a solution that has less privacy but more deployability.
Thank you very much, Kasra. Moving on to the next presentation.